Since this is an infinitesimally small change in distance, it should be an infinitesimally small change in the electric field. So since I have electric fields, I am going to apply Faraday-Lenz's law. The left-hand side of the equation is I'm doing a line integral. So I'm going to start at one particular point, and then I'm going to go around my circle there and figure out what E dot dl is, and I'm going to set that equal to this differential, or that derivative. Typically, the way you do it is a right-hand rule. Since magnetic field's coming out, I am going to go counterclockwise. So I'm going to start here. I'm going to call that A, B, C, and D. So Faraday's law, I'm integrating E dot dl is equal to negative d phi b dt. So this would be E dot dl along path A plus E dot dl along path little b plus E dot dl along C plus E dot dl along D. And that should be equal to the negative equals negative d b dot a dt. I guess it would be, yeah, with that. All right, so doing dot products here. I have 4 dot products. dl is a vector going in the direction in which I'm doing my line integral. So for A, dl subscript A is in that direction. Basically, it's dx. What is the dot product between the electric field and dl along path A? The electric field's going this way, dl's going that way.
Into the board.
Say it again.
Into the board.
Nope. We're doing dot product, not cross product.
Oh. It would just be up and towards the right.
Dot products are scalar products. You notice also the right-hand side, that's a scalar right there. So that better be a scalar. What is a dot product?
Just 2 vectors times each variable and then add it together.
Okay, which parts do we multiply together?
Yeah, multiply i's together, multiply j's together.
Okay.
So,
So in rectangular form, absolutely. So you're multiplying the parallel parts. So if my electric field is going this way and dl is going that way,
0.
0. Because my electric field is perpendicular to dl. Which one, other one is equal to 0? Which other term? Yep. So I'm now left with these two. Here, I have E going in the same direction as dl. So this would be E plus dE. Dot, actually, H is a scalar. Plus this, well, E is going up, but dl subscript little d is going down, because again, I'm going around in the path, in back where I started. This would be negative E H. That's going to be equal to this. So the only thing that is really changing in here is the magnetic field. Magnetic field here is not the same as here. My area is set because I set it. It is a width of dx and a height of h. And so my area, so this becomes negative area dv dt. I'm just making my area vector the same direction as the magnetic field. And so this would be negative h dx times dv dt. On the left-hand side of my equation here, I have EH plus HDE minus EH equals negative HDX times dVdt. Well, two of the terms cancel each other out because I got EH and negative EH. Equals negative h dx times dv dt. I have h as a factor on both sides, so h's go away, which is nice because h is some arbitrary length, so if it didn't go away, this would probably be a worthless derivation. I'm going to divide both sides by dx, and so I have dE dx is equal to negative dv dt. So now I'm going to take that first equation there, and I am going to take the derivative with respect to x, and then I'm going to take the negative of the derivative of b with respect to time. So what is dE dx?
It's negative E naught cosine kx minus angular frequency t plus think variable
Phi.
phi.
The phase is phase shift. To account for the fact that not everything starts at
Yeah.
0 or the amplitude. There's one thing missing here.
Okay.
Chain rule, take the derivative of the sign, and then take the derivative of what's inside here, so there should be a k popping out. And that should be equal to the negative. Well, now let's take the derivative of this with respect to time. And what do we get?
B dot negative cosine, or negative b cosine.
So negative b, I got this negative from here, and then I got a negative cosine of kx minus omega t plus phi.
Take k out, or no?
Not the k, take the derivative with respect to time,
Why do we keep the k out the first one though?
because we took the derivative with respect to position.
Oh, this is the time, okay. So W,
Omega.
Okay, thank you. There's still one thing missing.
Negative omega.
Yeah, negative omega times negative omega. So I have negative k e sub naught cosine of kx minus omega t plus phi equals negative omega e sub naught. I have three negatives there, so two of them cancel out, and I'm left with one, times cosine of kx minus omega t plus phi. So if this is true, well, actually, let's get rid of the negative sign since I have still on both sides. So if this is always true, then the coefficients must be equal to each other. In other words, the wave number times the magnitude of the electric field must be equal to the angular frequency times the magnitude of the magnetic field. Manipulating just a little bit, I'm going to bring k over to the right and take b naught over to the left. And so I get omega over k equals E sub naught over B sub naught. Since omega over k is the speed of the wave, I now have the fact that the speed of this wave is just going to be the amplitude of the electric field over the amplitude of the magnetic field. Do a dramatic pause for people to catch up and to ask questions.
Really stupid for asking this, but what did you just do?
What we've done is taken Faraday-Lentz's law, worked with the assumption that we have this electric magnetic field self-propagating, that changing one causes a change in the other, and they're self-propagating. We then applied Faraday-Lentz's law to a section of the electric field, or the electromagnetic field here,
For what reason?
in order to try to figure out how fast it's traveling.
Oh, okay.
Now, when Maxwell first did this, did he go through and go, I bet I can figure out the speed? Or was he just playing around and said, and after months that, oh, I think I can find the speed of this? I don't know. But ultimately, in the end, he found the speed of, using just Faraday-Lentz's law, he found the speed of the wave to be the magnitude of the electric field with the magnitude of the magnetic field. That's what we've done.
Wait, what, say that again?
We have found that the speed of, using Faraday-Lentz's law, found the speed of the wave, of this wave, to be the magnitude of the electric field divided by the magnitude of the magnetic field. We were halfway there.
Halfway there?
Yes.
Halfway where?
To coming up with a better speed.
Okay.
Or
The velocity. Velocity, right?
No, speed, find speed. V without the vector symbol is speed. Put the vector on top of it, it becomes velocity.
Amplitude of the electric field over the amplitude, which is magnetic field.
Yes,
Electric field.
they're probably less of a tongue twister than magnitude of the magnetic field. You might have guessed. We probably should take Maxwell's contribution at some point. So we're going to do the very similar process, except we're going to use the Ampere's Maxwell law. Ampere's law with Maxwell's correction. I need space. That done with. This time, so I have my electric field, so where I've drawn my rectangle there, my electric field is up, my magnetic field is coming out. I'm going to do something similar, except I'm going to tilt it. So my magnetic field is up, my electric field is going away from us. So if I did that, and then looked at section there, with a dx, a height of h, my magnetic field is B. This would be B plus some infinitesimal change, and my electric field is going away. And again, the first time magnetic field's coming at us, now we're looking at it, magnetic field's going up, electric field's going away from us, just changing our point of view. Again, we're going to be doing a line integral here. In other words, we're going to be adding some stuff up. Again, right hand rule, since electric field's going into the board, I'm going to go around clockwise. So I'm going to start here, and then go up, little b, c, and d. So I go around clockwise. Now, there is no traditional current here. I don't actually have charges moving, and so the first term here goes away. So what I'm left with is just the line integral of the magnetic field around this loop is going to be equal to that. So the integral of B dot dl equals mu naught epsilon sub naught d phi epsilon sub naught dt. So this is B dot dl along path A plus B dot dl along path rho B plus B dot dl along path C plus B dot dl along path rho D. And that's going to be equal to mu naught epsilon sub naught times the derivative of the electric flux there. Very similar to what I did last time, except BCE switch. My area is not changing with time because that is a virtual physical disk area, so area is going to pop out. Over here, for the same reason as before, B dot dl along path B and D are 0, because along B, I've got my electromagnetic field going up and my line part, the dl, going to the left, or your right. And then along path D, I'm now heading magnetic field still up, and dl is going to your left. So that is 0, that is 0. So in that first segment, I have B, H, plus, and along here, my path, my dl is going down, but my magnetic field is going up, so negative B plus dB times H. And that's going to be equal to mu naught epsilon sub naught area times dB dt. Over here, I have BH minus BH minus HdB equals mu naught epsilon sub naught HdX, that is my area, times dE dt. Obviously, got some canceling out there, so I have negative HdB equals mu naught epsilon sub naught HdX times dE dt. So I'm taking, oh, well, we'll wait on that. H goes away. And then I divide by dx. Same process as before, except now I end up with negative dB dx equals mu naught epsilon sub naught dE dt. And now we will take derivatives. Woo! What is dB dx?
Something.
Let's see if we can narrow that down.
Negative E naught K cosine insert formula.
Equals mu naught epsilon sub naught, and now dE dt.
Negative E sub naught. E? Would it be E or B?
E.
You happy now?
Yeah.
Okay.
Cosine. I guess there's a K there too.
No.
No? Okay, this time?
With respect to time,
Oh, so like negative W, negative frequency.
negative omega. W. Omega. Clear.
Yeah.
Especially when I do it fast. Then kx minus omega t plus 5. So I got two negatives here, they will cancel out. I have two negatives here, they will cancel out. And so if these are equal to each other at all times, then the coefficients must be equal, so P naught K must equal mu sub naught, epsilon sub naught, omega E sub naught.
It's a lot of
We can
knots.
substitute omega, right?
What do you want to substitute in for omega?
The speed, but we're still trying to.
Yeah, I guess,
Substitute for V and K. Wait, no, I'm trying to find.
we can, sure.
Are we finding the speed?
Yeah, we're gonna find speed here. We're gonna get something a little bit different than that. But, yes. But they have to be equal to each other. And that's what power comes in. All right. So you wanted to substitute omega for what, VK?
I guess, yeah.
So B sub naught K equals mu sub naught, epsilon sub naught, VK, E sub naught.
K's cancel.
So I'm left with V is equal to B sub naught over E sub naught, U sub naught, epsilon sub naught. But that also has to be equal to E sub naught over B sub naught. But just because I use two different equations, if those equations are valid, the same, if I get two equations for speed, those equations have to be equal to each other.
So we got V equals 1 over mu epsilon naught.
Close. All right, so I want to get all these on the one side, so I'm going to multiply by the reciprocal. So I have 1 over U sub naught, epsilon sub naught, equals E sub naught over B sub naught squared. And since E sub naught over B sub naught is just my speed, that's V squared.
Okay.
So therefore, the speed of an electromagnetic wave is the square root of 1 over mu sub naught over epsilon naught, or 1 over the square root of mu sub naught epsilon sub naught. If we plug in our modern values here, that's 1 over the square root of 4 pi times 10 to the negative 7th
Yeah.
times 8.85 times 10 to the negative 12th.